For his astounding commitments to the fields of material science, Kaku has genuinely mentioned that the James Webb Space Telescope has seen 6 gigantic planets that experts acknowledged were unequipped for existing. These appraisals have the legitimacy to open up new perspectives on the way in which we could interpret the universe. The straightforwardness is both enrapturing and submissively testing existing speculations about the new developments and improvement of universes. It infers an incredible arrangement to pay special regard to these updates, and the assertion by such trained professionals highlights the significance of these disclosures. Kaku is an astounding figure in the logical field, a physicist of American and Japanese legacy. He is seen as an expert in both normal material science and quantum mechanics. Rather than some more moderate and precarious subjects, Kaku has been available to the astonishing, prideful possibilities of the James Webb Space Telescope mission. His energy to embrace new discoveries and share them with the public shows his commitment to propelling our comprehension of how we could decipher the universe. We are appreciative that this unmistakable master has chosen to end his quiet and straightforwardly share what can no longer be denied. The powerful, clear tone of the remarkable physicist is clear in his remarks on the disclosures made by the James Webb Space Telescope, giving the possibility that this has been an advancement that has reignited his interest. Join us as we investigate the repercussions of Kaku's transparency about these 6 titanic plans. Kaku is a master who has consistently had the limit to contemplate new theories throughout his life. He has shown a responsiveness to thoughts that challenge ordinary thinking, grasping that Einstein's hypotheses of relativity and Newton's regulations, while basic, are restricted in completely grasping the universe's complicated plan. Kaku believes that the disclosures of the new telescope could impel the area of cosmology. However, a considerable lot of his partners still can't embrace this view. This has caused concern and misgiving among Big Bang researchers and pundits of quantum mechanics. However, this only draws chuckling from Kaku. The James Webb Space Telescope has uncovered 6 colossal universes tracing all the way back to the earliest seasons of the universe. Each of these huge frameworks contains more stars than our own Milky Way, notwithstanding having formed simply 200 to 700 million years after the Big Bang. The gathering of cosmologists who made the disclosure has named these brilliant vast frameworks universe breakers. If confirmed, they would fundamentally change how we grasp the universe. The aftereffect of these disclosures is significant, suggesting that the universe's early years were undeniably more unique and complex than recently thought. The hypothesis of how things started lets us know that the universe was turbulent after the Big Bang. The main strong items took a long time to form, and it took much longer for these items to reach adequate thickness and produce light. The advancement of perplexing designs like cosmic systems was remembered to have occurred much later. A portion of the as-of-late found colossal frameworks outflanked the Milky Way in size, and their huge brightness suggests they were possibly framing many new stars every year, while our universe structures stars as it were inconsistently. It remains hazy precisely at the point when the principal structures formed, and specialists have not yet settled this. One thing is clear: toward the start, there might have been just person stars or gatherings of stars that eventually coalesced into larger designs over time. More modest frameworks supported bigger, more huge designs. Previously, it was trusted that such huge and complex frameworks were unequipped for existing at that time, which raises the question of whether the universe is a lot more seasoned than recently acknowledged, or if such huge frameworks formed much sooner than guessed. This situation is troublesome to accommodate with conventional science, which still finds issues with this model. Some areas of material science have explicitly excused these revelations and scrutinized the exactness of age estimates. Kaku is aware of this and had this to say: "There are various models and obsolete hypotheses that continue in view of the impact of certain well-informed specialists. Many of these hypotheses were logically exposed when key examination uncovered their defects. Reality in any science, particularly in material science, lies with the work of experimentalists who keep the hypothesis sharp and on target." He went on, "Here on Earth, we have very little information about the genuine starting points of the universe. This explanation highlights the significance of constant testing, refreshing, and reaffirming in the logical cycle. The hypothesis of how things came to be was first illustrated in 1927 in light of perceptions of the universe's extension. This data prompted the end that the universe began from a solitary boundlessly thick point and has been extending from that point forward. At the time, it was hard for individuals and researchers to envision a universe with both a start and an end. The plausibility of an immortal universe was outside human ability to grasp. Even today, researchers still struggle to completely understand it. However, it is essential to consider these potential outcomes, regardless of whether the new disclosures don't line up with what specialists have acknowledged for quite a long time. As for the hypothesis of how things started, science has shown many times that reassessment and receptiveness to heavy ideas are critical to the logical interaction. For example, when Einstein was young, it was once accepted that stars and planets were fixed in the universe and that these specific arrangements consumed a defined space. However, now we know that everything in the universe is moving. Planets orbit stars, stars move inside their worlds at paces of a few kilometers per second, and entire worlds move quickly through the universe, whose extreme destiny we still can't predict. This astonishing understanding of the universe challenges long-held convictions and highlights the need for continuous inquiry and change in our logical reasoning. Today, researchers are challenged to recognize irregularities and establish that hypotheses are lacking until they have been totally tested or affirmed by observational data. The possibility of the Big Bang emerged from the observation that worlds are moving away from one another, and this distance is comparative with their division from Earth. This theory, known as Hubble's law, suggested that the universe was expanding over time. Factors like vast microwave background radiation and the red shift of light from far-off worlds, alongside other cosmological patterns, seem to support this theory. However, it is important to remember that before, people who believed the Earth was flat and that the sun rotated around us also had observational proof for their convictions until new events or technological advancements came along that gave a clearer picture. Right now, we are seeing a comparable situation. Scientists predicted the new James Webb Space Telescope would confirm questions related to the theory of how things became, but in all actuality, they have countered these 6 tremendous frameworks that seemed impossible. This shows that science is continually advancing, and specialists should stay open to new disclosures and rethink existing hypotheses, considering the available proof. The surprising revelations have tested current understanding and provoked a reassessment of well-established cosmological speculations. Researchers utilize redshift as a tool to process various estimations in the investigation of the universe. Redshift, otherwise known as the Doppler effect, refers to the change in the shade of light as light sources and spectators move relative to one another. To comprehend this, imagine stopping and hearing a car moving toward you. As the car draws nearer, the motor gets louder. However, when the car passes or moves away, the sound changes. This happens because the sound waves change as the car moves. The same is true for light. When a light source like a far-off star approaches us, the light moves to bluer tones. On the other hand, when the light source moves away, the light moves to redder tones. This phenomenon is called redshift. Physicists have converted redshift values into percentages and distances for estimation in the investigation of the universe. However, it is important to note that even a small mistake in these estimations can have significant consequences. The previous evaluation procedures are now under review. The latest disclosures related to our universe require consideration of whether they are truly based on redshift errors or if some scientists are simply dismissing current realities. This is a question that requires careful assessment and a thorough review of the data and methods used in the investigation. The continuous assessment and reassessment of measurement methods highlight the growing understanding of continuous inquiry. Thank you for watching the video. As always, we remind you to post your requests in the comments section. If you enjoyed the video, kindly hit the like button and share it so it reaches more people. Also, subscribe to the feed so you don't miss more content like this. Thank you again for watching, and we'll see you in the next one. This call to action encourages viewers to engage with the content, fostering a community of inquisitive minds eager to explore and understand the latest scientific discussions. The investigation of our universe, with its vast distances and complex bodies, continues to astonish and challenge scientists worldwide. From early theories about the universe to the latest discoveries made possible by cutting-edge technology, each revelation reshapes how we might interpret the universe and expands the boundaries of human knowledge. One of the most critical and enduring questions in cosmology revolves around the origin and development of galaxies. Galaxies are like vast cities of stars, gas, dust, and dark matter bound together by gravity. Understanding how galaxies form and evolve is vital, not just for unraveling the mysteries of our universe, but also for testing or confirming existing theories. For instance, the Big Bang Theory, proposed nearly 100 years ago, suggests that the universe began from a single, vastly dense point and has been expanding ever since. This idea arose from observations of the universe's expansion and the cosmic microwave background radiation, considered remnants of the early universe's intense energy and light. However, recent discoveries, especially those made by the James Webb Space Telescope, JWST, have challenged some key ideas fundamental to the theory of how things came to be. The JWST, with its remarkable sensitivity and resolution, has identified galaxies that appear far larger and more developed for their age. One such discovery includes 6 large galaxies dating back to when the universe was only 200 to 700 million years old, a mere flash in its 13.8 billion-year history. These galaxies, named universe breakers by the research group, challenge conventional thinking, as they are already so large and bright at such an early cosmic age. The discovery of these galaxies raises fascinating questions about the rapid development of the early universe, challenging existing models of galaxy formation. According to prevailing theories, galaxies form slowly over billions of years through the merging of smaller systems and the accumulation of gas and stars. The existence of these massive galaxies so early in cosmic history suggests a much more complex and possibly faster process of galaxy evolution than previously thought. Moreover, the discovery highlights the crucial role of technological advancements in reshaping how we understand the universe. The JWST's ability to peer deeper into space and capture faint light from distant galaxies has allowed cosmologists to uncover previously invisible pieces of the universe's early development. These insights provide valuable clues about the conditions and processes that govern galaxy formation during the universe's early stages. The implications of these discoveries extend beyond cosmology. They challenge scientists to revisit and refine existing cosmological models to better account for the observed diversity and complexity of galaxies across vast timescales. They also highlight the dynamic and evolving nature of scientific knowledge, where new discoveries can spur future breakthroughs and open new avenues for research. As scientists continue to examine and interpret data from the JWST and other observatories, the study of galaxy formation remains an exciting and rapidly advancing field. Each new discovery brings us closer to unraveling the mysteries of our origins and helps us understand the fundamental processes that have shaped the universe as we know it today. The continuous advancement of observational technology has revolutionized our understanding of the cosmos. The James Webb Space Telescope, JWST, is at the forefront of this revolution, enabling us to peer deeper into the universe's history than ever before. The insights gained from this telescope offer new perspectives on the formation of galaxies, stars, and other cosmic structures. These breakthroughs are not just reshaping our view of the universe's past, but also challenging the very frameworks we use to understand cosmic evolution. One significant consequence of JWST's discoveries is the reevaluation of the role dark matter and dark energy play in galaxy formation. Dark matter, which accounts for the majority of the universe's mass, remains largely mysterious. While scientists understand that dark matter exerts gravitational forces on visible matter, its exact nature and how it contributes to galaxy formation are still unclear. The newfound galaxies, which appear more developed than previously believed possible for their age, may provide valuable clues about how dark matter influences early cosmic structures. Furthermore, these discoveries have spurred a renewed interest in the rapidity of star formation in the early universe. Prior to the JWST findings, the prevailing model suggested that stars and galaxies form slowly over vast periods, with the first galaxies emerging several hundred million years after the Big Bang. However, the discovery of highly evolved galaxies at an early cosmic age suggests that star formation may have been far more rapid than previously thought. This opens up possibilities for new models of how the earliest stars ignited and began shaping the universe's structure. As the JWST continues to send back unprecedented data, scientists are refining their models to account for the surprising complexity and variety of galaxies in the early universe. These findings reinforce the importance of technological innovation in science, demonstrating that each new discovery has the potential to significantly alter our understanding of the cosmos. The ongoing study of these phenomena promises to reveal even more about the fundamental forces that have shaped the universe and will continue to drive the exploration of deep space. As the James Webb Space Telescope, JWST, continues its groundbreaking mission, the astronomical community is grappling with the profound implications of its findings. These revelations have forced scientists to rethink long-established theories and embrace new paradigms. The ability of the JWST to detect light from some of the earliest galaxies, far beyond the reach of previous telescopes, offers a deeper glimpse into the universe's infancy, challenging assumptions about its timeline and the processes that shaped it. One of the most compelling aspects of these discoveries is their potential to reshape our understanding of the first billion years after the Big Bang. The rapid formation of galaxies, as observed by JWST, suggests that the conditions in the early universe may have been far more conducive to galaxy formation and growth than once assumed. This challenges the view that the universe's early years were dominated by chaos and slow development, instead hinting at a more dynamic and accelerated process. In addition, these findings have raised intriguing questions about the role of supermassive black holes in early galaxy formation. Supermassive black holes, which reside at the centers of most large galaxies, could play a critical role in regulating star formation and influencing galaxy evolution. As more data is gathered, the role of these enigmatic objects in the universe's development may become clearer, providing essential insights into how galaxies evolve over cosmic time. The ongoing research fueled by JWST promises to drive future breakthroughs in understanding the universe's origins.